Hello. Today I'm presenting some modeling work that I've done to improve the S&C performance and reliability within Network Rail. What I've found after joining the S&C team 2 years ago, actually it's 2 years ago today that I joined the S&C team, what I've found is that we may design a component or layout that we think is perfect, but if it excites the resonance frequency of the train or causes unnecessarily large forces, then it's not a good design. So the modeling and data analysis tools that I use is Vampire and TrackX. So these are vehicle dynamic simulations packages. TrackX is an in-house Network Rail in-house software based on Vampire. It runs on Excel, so anybody can use it. So vehicle dynamic simulation, this was developed by British Rail in the 70s and 80s. It assumes that the train is made up of masses and springs and dampers. So it's a rigid body motion method, and then it has a contact patch modeling, and then the track model as well. So you combine everything, you can calculate the response of a vehicle and also the forces at the contact patch. So the forces will dictate the degradation of your track. So that's very important. So this example is an animation from Vampire. I got it from Delta Rail Alan Minis. Thank you. So it shows this shows the train running through the crossing. I'll play it again. So the forces, you can see a quick jerk as it goes through the crossing. So it shows the forces at the wheel there. So you can see arrows coming down, up and down under the wheel. That's the forces acting on the rail. So you can use it to calculate forces and the response of the vehicle and see if the design is good or not. Okay, so that's the animation. So other tools are the CAD and finite element modeling tool, SolidWorks. I use it to calculate stress on components, and also to do some assembly motion analysis. So the picture there shows an example of my work. I was looking at the effect of lipping on the stock rail that's acting on the switch rail. So if you push the switch rail, what is the switch rail seeing? So this is one example. And this is a switch flexure model that I'm looking at. So I can put a force anywhere along the switch blade and see what the reaction force is at the back of the switch, and also what the stress level is at the cutout at the foot. I'm also looking at the supplementary backdrive. This is a model of the supplementary backdrive for a CVS switch. So the graph there shows the reaction force on one of the crank bases. Okay. So, and the third software package that I use a lot is MATLAB. It's like a high-level programming data analysis package. So I use it for collecting data, plotting graphs, and processing large volume of measured data. So the graph there shows rail profiles that I measured on track. I can have 500 rail profiles, and I just write a program in MATLAB, and you'll read the 500 profiles within a few minutes and plot them out. And the dots there are the contact position by a wheel. So blue and red shows, blue is the design profiles, red are the measured profiles. So you can compare the difference between the design and the measured profile. So I'll show a series of examples that I've done using all these modeling techniques. So example one is the track design optimization. I do a lot of these work with Northern Hub, with David Woods, and Crossrail and the routes as well. So when they have a new layout, they want to know if the layout has been optimized. Because in track design, you have a wide range of parameters you can use. But is it the best optimized values that you're choosing? So my modeling using Vampire is to even out the wear and the RCF damage, which is rolling contact fatigue, at all the wheel sets. to avoid high localized wear, because if you have high localized wear in RCF, you need to change the rail. So the whole life cost becomes quite high. Okay, so this is an example that I've done with David. It's also lane proposed option 20. So there are 6 routes. There are the up and down Chat Moss, up and down Bolton, and 2 siding tracks. So, so from the simulation, the output would be the wear. So that's the energy transferred to the rails. That shows the wear rate of on the rail. And then you have the RCF damage. So would you have cracks and all that if you have this design? So I use a traffic light color code to present the predicted severity of the damage. So it's the green, amber, and red color codes. So for example, down Chatmoss, I was given this. You have all the elements, the speed, the radius, and the applied cant, and the cant deficiency. So I did calculations using, oh my God. Did I turn it off? Yes, my knight in the shining armor. So, okay, I better not move too much. So this is the example that I did. I did the wear calculations, I did the RCF calculations. I looked at both the low rail and the high rail, and the flange, the gauge corner as well, and I proposed changes to the design. If I can't change anything, I'll propose maintenance regimes. So for example, this part of the rail will experience a lot of RCF problems, then use premium rail for this part. And if it's wearing too much, put some lubricators here. So I propose things for different sections of the track. Okay, so recommendations, lubrication, cant deficiency. Usually I maximize the cant deficiency because increasing cant deficiency is good because the train would be more radial when it's curving. So more radial means you exert less force on the high rail. Okay, so more even force, not at the leading wheel. And then you preserve the low rail, because the low rail will suffer from plastic flow, corrugation if you're over-canted. So with those problems, you can't do anything with plastic flow. You can't mitigate it. So if you increase the cant deficiency, you save low rail. So the result from all these studies is that it's easier construction because we have lower cant. It helps with the gauging issue as well with lower cant. And also we reduce the wear and RCF damage on the rail, and so therefore less maintenance and lower whole life cost for the whole layout. So this is the second example I'm presenting. It's new switches at risk of causing derailment. I was asked to go out on site 2 years ago to help hold back junction in Leeds because a new set of EV switch has failed the inspection. The inspection means that you put a TGP8 gauge on, which is the one shown on the right. There's a line there. That line shows 60 degrees. So if the contact position falls anywhere below the line, it means that the contact angle is less than 60. If it's less than 60, there's a risk that the train will derail. So this is our inspection regime. And this new switch failed inspection. So what is the cause of it? So I did some wheel rail interface analysis and found that, and took measurements of the profiles, and then I used Vampire to look at it, and indeed the contact angle is 56 degrees, which is, the action would be to ban all facing traffic. So that's a lot of delay minutes and cost. So investigating this case, we found that the root cause was because of the loose machining tolerance specified in the relevant standard. The standard was 4004. So what we then do is to change the standard. We issue a letter of instruction, 283, to all S&C manufacturers in February 2013, and we tightened 3 main dimensions because there's so many machining tolerance on the switch. If you tighten everything, it will be so expensive. You won't be able to make the switch. So we only target 3 of them, the key dimensions. So with the targeted 3 key dimensions, the contact angle will not be less than 58 degrees. So one example of the dimension was the gauge corner radius. The radius is 12 mil, but the tolerance was plus minus 2 mil. So that gave 5 degrees. That is the main reason. But if we change it to 0.25 mil, plus minus 0.25 mil, we could do that because nowadays they CNC machine the rails, not planing it. Okay, so that plus minus 2 mil was like 20 years ago. So we also found that this loose machining tolerance has an effect on switch blade damage. So this figure here shows that using those measured profile, I run a vampire analysis and showed that with design profiles, the last contact on the switch blade in the trailing direction is 600 mil from the toe. At that position, the switch rail is 8 mil thick, so it's good. But with the measured profile, I run the same simulation and the contact position is actually at 140 mil from the toe. And the width of the switch is 4 mil. So that's why sometimes we have switch blade breaking off because of the tolerance issues. So loose machining tolerance can also cause premature switch blade damage. So the result is, this finding, we have now reduced the derailment risk with new switches. And then there are fewer SO53 inspection failures because of that, and the associated delay minutes by banning the trains, and also the remedial grinding work that has to be carried out. And also we reduce the incidence of premature switch blade damage. So the example 3 is the switch topping design and derailments. We have at least 6 different switch topping designs in our suite of S&Cs. The topping design means the relative height between the stock rail and the switch rail. So what we found is that when we ask people to go and repair the switch, the grinders go out and they start grinding the switch down. There's no limit how much they can grind to, so they keep grinding it until the topping depth is quite low. So what is the unsafe depth until a wheel can start climbing up the switch? What is the relevance of this? In Princess Street Gardens, the derailment that happened in 2011, the switch rail was very, very low. It was about 27 mil low, lower than the stock rail head. Okay, so I plotted all the topping designs as well as the topping at Princess Street Gardens and Shrewsbury. It shows that at the limit of 20 mil, it becomes unsafe. So at Princess Street Gardens, the train derailed around a topping depth of 23. At Shrewsbury, it derailed at around a topping depth of about 21 mil. So there is a limit. So we're setting a new grinding limit. If you find the switch topping being 20 mil or below, 20 mil or deeper, then that's it, no more grinding. You have to well repair to build up the switch. So this is published in a new letter of instruction last week. So in the topping design again, we have this straight switch, straight type switches. As you can see, it's just a straight line and a straight line going out. These are the old switches. So we had a couple of derailments on these switches. And we found that actually we have 3 different topping designs by 3 manufacturers. So we need to standardize the topping design to make it safe. So I did some vampire analysis to assess the wear and derailment risk. So these are the drawings, the REPW drawings for these switches. It's done by hand. So you have like notes protruding from the drawings. Don't use this, use that. So there's different interpretations of these drawings by the 3 manufacturers. So I did some analysis and we standardized it as progress rail topping. So we will reduce the risk of derailment and wear. So the result from this example is that a better understanding of switch topping designs and therefore able to reduce the risk of derailment by changing standards and drawings. Example 4, switch grinding practice. As we saw previously, that new switches, people are going out to grind it down and all that. And I realized that the grinding process is that you have to grind down the switch to the design blade angle, which is 76 degrees. So this switch here has a contact angle of about 44 degrees. So to get it to 76 degrees, which is specified by our standard, you need to grind off at least 5 mil of the switch. So that is effectively reducing a lot of material off the switch just to make it compliant. And that involves 30 grinding passes. So it takes a whole night just to grind it down. So I did some analysis and then I said, okay, let's change the practice. We'll grind it to 65 degrees instead, minimum of 65 degrees. So I did an analysis, it's all fine. 65 degrees, 60 degrees is the limit, 65 degrees has some factor of safety in it. So, and also we only target 20 mil depth down to 40 mil depth, because beyond 40 mil, the wheel will not see it. So that will reduce a lot of work being done, like rush job by the grinders trying to get everything done and then open to traffic. So there's no more rushing around. Just make sure you blend everything, make sure there's no discontinuity between the work and what was there before. So that is the requirement. So this is published in a letter of instruction. So using the measured angles, we came out with maintenance limits. So this is again in the same letter of instruction. So anything below 55 degrees contact angle, just ban any traffic. Because derailment at Stroh Street, the contact angle was about 52. So even if you lubricate your switches very well, the wheel will still climb. So anything between 55 to 60, then you can do as what the inspection standard says, apply some lubrication, grind within 36 hours. And between 60 and 65 degrees, as in new instructions, try and grind within 13 weeks or monitor the wear every 13 weeks to make sure that it doesn't go below 60. So this is our new maintenance limits. So the results from this work is better guidance for maintenance, therefore reduce the risk of derailment due to rush repair work. And also less grinding is required, so you reduce the cost in labor as well as material. You don't have to replace that switch that often. Example 5, relaxing the FPL tolerance, the front point lock tolerance. I was asked by the routes if we can relax the tolerance a bit. At the moment, it's lock at 3.5 mil and detection at 5 mil. If we can increase the tolerance, then we have more. We can run more trains. We won't have that many point failures. So I did some wheel-wheel interface analysis, because this is an important issue, because relaxing the FPL tolerance could increase the risk of train derailment, because the train wheel might strike the switch. Well, it might not just climb immediately, but the rest of the train might climb because the switch is being flattened and creates a running table for it to run up. So I did some wheel-wheel interface analysis, and I found that the switch gap is 3.5 mil for vertical switches. That's how far you can open the switch until the wheel strikes it. But that's using a new P8 switch, new P8 wheel profile. If you have a worn wheel, that gap will reduce because the flange face of the wheel is steeper. So in fact, we are near the borderline case. So I did all the analysis. Although with NR60, you can relax it a bit, but with worn wheel, you will reduce it. So in fact, I don't recommend it to be relaxed. In fact, should we tighten it? So example 6, common crossing profiles optimization. Our design of the common crossings are generally over 40 years. And vehicle characteristics have changed in the 40 years. So we're proposing some changes to the current design. This is an example of a crossing at Shelford Junction. We paint spray it and see what the train was doing across it. The train was running from the left-hand side to the right, transferring from the wing to the nose. There's a strange gap at the nose. It's hitting the side of the nose and there's a strange gap there. So we investigated what was happening there. So I'll show you the results after, but we have a problem at that rail because our crossings are failing between 5 and 10 years of service. Crossings are designed to last at least 20 years. They're meant to last for 450 million gross tons, but they're lasting less than that at the moment. So what is the reason? The possible reasons are we're increasing our traffic volume, and we're increasing in line speeds, and we have less access for maintenance. So something has to change. We renew our layout configurations, changing it from timber to concrete. That increases the track stiffness. So we don't understand the pads and all that enough to make it replicate what the timber was doing. Our crossing designs, as I said, shopping designs have not changed since the 70s. That includes the 113A and the NR60. Topping was optimized for P1 wheel profiles, but we now use P8 and P5. So we look at our issues. How big is our problem? So I looked into the RDMS, which is our rail damage management system, and found that in 1 year, November 2012 to November 2013, we had 9,500 crossing defects, common crossing defects. And we're struggling to close these defects. In fact, we closed 2,000 of them. So these are the main issues, the top 80% of the crossing issues. There are squats on the crossing, lipping, problems at the nose and wing transfer area. And 14th on the list, if you look at the right-hand most column, 14 on the list is vertical cracks on the foot of the crossing. So although it's 14 on the list, but it has big performance impact because we need to put an ESR on, emergency speed restriction on, and then we have to sometimes wait for 3 to 4 months before we can replace the crossings. So that is a big performance impact. So we now know that if we focus on a wheel transfer area, we can actually reduce 28% of our defects or more. Because I don't know where the squat casting, they could well be at the wheel transfer area. So focusing on the wheel transfer area, we're looking at the crossing foot, we're looking at the wing rail, and we're looking at the crossing nose. So the photos here shows on the left the wing rail indentation due to trailing moves on the crossing, and the top right shows squat developing at the wheel transfer area on the crossing nose, and the bottom figure shows the crack at the foot. So crossing foot flange design. We have these scallop design for most of our crossings, cast center block ones and cast monoblock crossings. So we're finding that cracks are forming at where the scallop goes in. So can we change that design? We have continuous foot flange design used for cast center block crossings wider than 1 in 15. I think this was because we used to use rail sections just bolted on, hence they have continuous foot flanges. So perhaps we should specify continuous foot flanges for all crossings, not just for selected few. So it will increase the stiffness at the foot region. But if you flip the crossing over, you can see that there's a massive section with lateral material there. So where do you think the crack will form? So we have to look at the crossing design as well at the base, whether it's longitudinal ribs or lateral ribs. So now for nose and wing topping designs. We have two types of wing designs, flat wing rail and inclined wing rail. So the photo on the left shows the flat wing rail design. So the wing rail is effectively flat. And the inclined wing rail design has a slope 1 in 20. So we'll contact the crossing nose. If you look at the graph on the left, that's the flat wing rail design. You can see that the wheel is less supported at the wing rail. There's very little contact there. And if on a curve, it actually strikes the nose. There's some overlap at the nose. Whereas on the incline profile on the right, you can see that there's more support on the wing rail, and there's very little overlap at the nose. So inclined table design seems to be better. It reduces the damage to the crossing nose. It provides more support on the wing rail and moves the wheel transfer area to where the crossing nose is bigger, behind the tip. And also, you have a bigger cross section at the wing. Perhaps this will increase the rigidity at the foot. Wing rail support. The amount of wing rail support is determined by the width of the wheel and the wing rail design. I think I was speaking to people who had worked for British Rail and all that. I think the size of the width of the wheel has been reducing over the years, perhaps to reduce the unsprung mass and the material. So the graph on the left shows the wheel transfer for a 1 in 6 crossing. So if you have an inclined wing rail design, the wheel will still transfer fully to the nose after 100 mil from the nose. So this is a summary of what I've said, the wing rail support. With sharp angle, the wheel transfer is near the nose, near or at the nose. And there's a large dip angle and therefore impact forces. But with a flatter angle, the support is provided by both the wing and the nose for a longer distance. Therefore, there's less damage to the nose for a given speed. So, example of wheel transfer. So these are the sites that I've been to and spraying paint and all that to see what's going on. So the red line shows the overlap between the transfer of the nose and the wing. You can see that this is the 1 in 4.5. The transfer is almost immediate to the nose. So yeah, so the nose, where it's very, very thin, it's bearing all the weight of the wheel. So on the right, you can see the two designs. They're similar crossing angle, but the transfer length is very different. They're both inclined designs, but the transfer length is very different. The top one is a manual crossing. So you can see the wing rail is quite thin. So I'm looking into the different types of designs and looking at what is the optimum wing rail design as well. So what is clear is that the wheel transfer all occurred at the crossing nose. So as I mentioned, wing rail and crossing nose has to work together to optimize the wheel transfer at the crossing. In our drawings, we have a slope of 32 times crossing angle slope at the nose. Presumably, this is for easy measurement with a straight edge when you go out, when you repair the crossings and all that. So this hasn't changed for a long time. So the wheel coming to the nose will just go up the slope like that. So can you see where the topping ends in the photos? So that answers your question for why is there a gap at the running band? The topping ends there. So in fact, the wheel is going up a ski slope and then jumping and causing more damage to the nose. And you notice that it all happens on one bearer. So this will damage the track support system. Voiding and all sorts will develop. So I did some simulations with a modified wing rail and nose design. And then it shows that if you optimize the wing and the nose profile, you can actually reduce dynamic forces to a third. You're solving the root cause of the problem. What we have also noticed is that there's a lot of sight batter on crossing nose. So I got this photo from Dave Pete. This is at Drake's power station. A new crossing is experiencing sight batter. So it was apparent that the track rail wasn't doing much. So if we look at the worst case wheel check gauge, it's 1394.8 mil. For normal running, so we don't take the extreme case, it's 1392. And for passenger stock, it's 1390. But what are we building our check gauge? We are building our design check gauge between 1388 to 1392. So does it cover that wheel check gauge? No. So in vertical S&C crossing nose and wheel, the crossing nose and wheel can overlap by up to 6.5 mil. So it is possible for the wheel to be striking the side of the nose. EDH Common Crossings. I was asked to go out to this site like 2 or 3 weeks ago. We have a new EDH crossing that's banging, they call banging, and voiding is developing. So the problem is believed to be false flange damage. So you can see that the running band just changed abruptly from the nose to the leg ends. So we put a straight edge on the crossing. Actually, there's a dip there, as you can see from the in the photo, which caused sort of at where the running band suddenly changed. There's a dip there. So we measured some profiles, and then we found that at where the running band changes, there's a dip in the gauge corner. I call it flattening of the gauge corner. Sudden flattening of the gauge corner. So what it means is that as the gauge corner disappears, the wheel just falls down. So that's causing the banging on the EDH crossing. This is using a worn P8 profile. It's not even, it doesn't have false flange, it's just a worn P8 profile. You can see that it's crashing down. Using a new P8 profile, it crashed down further, it's 1.5 mil instead. So a new wheel would be worse. So did some simulations to show that, yes, indeed, you have higher dynamic forces because of this sudden change in the running band. So I'm still working on common crossings. I'm changing the wing rail and the crossing nose design. This is from SolidWorks. It shows the wheel going past from the wing to the nose. There's a dip angle there. I need to improve this dip angle, optimize it. The top graph shows the forces. But meanwhile, I've proposed solutions for our cast crossings. In the short term, specify all crossings with incline wing rail designs. So it will help with support on the wheel. And then specify continuous foot flange designs where we can. And also I will be specifying new crossing toppings without the 32 times angle slope. And also we're recommending tightening the flange way to 38 mil. At the moment it's 41 mil for check rails at sites with persistent sight batter of the crossing nose. So we much rather prefer the check rail to be worn than the crossing nose. And also we have made our first HP premium rail check rail. So that should be more wear resistant. And also we are specifying manufacturing tolerance for the running table of crossings to make sure that we don't see any more banging. So the medium term, we will be looking at the base of the crossing to increase or reduce the rigidity. And as Ian said, we are looking at rail pad optimization and also under sleeper pads. In the long term, maybe look at different crossing materials. So the result from this work is that we're aiming to reduce the impact forces at the wheel transfer area, which would lead to longer crossing life. So we reduce voiding and therefore maintenance activities. And there will be less well repairs and possession time. And we can reduce the risk of cracked crossings and therefore ESR and associated performance issues. This is the last example. It's about check rail heights on obtuse crossings. So what is the issue? The EN TSI proposed EN TSI addition comes up with all sorts of equations. It takes into consideration the geometry of the track, wheel, bogie, and wheel crossing interaction. So it specifies the height of the check rail that we need to have. So are we compliant? What I found is that our raised check rails are generally not compliant with the new proposed EN TSI standard. Because if the TSI standard comes out and we're not compliant, that's law. We have to do something about our crossings. That's too late then. So obtuse crossing, there's always a necessary gap at the obtuse crossing when a train goes past it. So we need check rails to help guide the wheels. So this is a raised check rail of 38 mm, so it has more guidance at the back of the wheel. If you have a normal check rail, the guidance length is shorter. If we have a bigger wheel, the guidance length is longer. So we like big wheels. We don't like small wheels on obtuse crossings. So work is ongoing, as doing the same thing with the common crossings. I'm trying to optimize the topping. As you can see, there's a big dip angle as the wheel goes from the knuckle to the nose. So we're trying to optimize this because we have a lot of obtuse crossing failures at the moment. So this is what we're trying to do, optimize the crossing so there's not much dip angle as in the simulation. Okay. So what do we have on our network? 38 mm? Yes, our standard says the maximum height on our check rail is 38 mm. So these drawings shows that most of them are 38 mm. So the ENTSI standard, the equations, if we plot it in terms of charts, this is what it looks like. So you have the y-axis, the minimum wheel diameter, and the bottom, the diamond angle. And the different color lines on the chart is the height of the check rail. So for the ENTSI standard, the maximum height of the check rail is 60 mm. But we only have up to 38 mm mostly. So if we take an example, if we use the 30 mm race check height, which is the green one in the middle, so if any of our wheel diameters are over there and any of our crossing angles are in there, it's good. Anything on the right-hand side, it's not good. Okay? So I program all the equations into MATLAB and I plotted the graph, actually the same graph. As you can see, for our SEN 56, all the lines move towards the left. This is because of the narrower gauge, 1432 gauge, compared to the SEN standard, the TSI standard, which assumes 1435. So all these little changes move the graph over to the left. So what is our minimum wheel diameter? For passenger trains, I think the minimum is 770. diameter. That's for the meridian, because they have inside fairings, so they have smaller wheels. But then we have freight trains as well, the FKA and FLA trains with very, very small wheels, which is beyond, smaller than what the TSI said. The TSI minimum was 500, but the FLA has 461 mil. So if we look at passenger stock, if we have 38 mil track rail height, we can only have that up to a crossing angle of about 6. So anything above, sharper than 6, we're non-compliant. So these are the FLA wagons with the smallest wheel. We have loads of these because the container wagons from Freightliner, you can't even fit a person underneath it. So an analysis results is that our crossings are compliant with the proposed ENTSI for passenger stock, sort of, but our crossings may not be compliant with for freight wagons. So, but does this mean that they're not safe? We haven't had any derailments at obtuse crossings yet. So maybe the TSI is over stringent, so we have to liaise with the RSSB to influence the standards. So current work using modeling, I'm investigating the crossing failures at Wessex, looking at specific sites like Weybridge, Great West, Vauxhall, and Feltham Junction. And I'm also collaborating with RSSB, as I said, on understanding the implication of a new TSI on raised track rails on our network. And I'm also redesigning profile of an NR60 switchblade to reduce the wear failures in a trailing direction. This is a known problem. Yes, the results should be out within the next 2 weeks. So conclusions from my work is that modeling can be powerful for improving systems and component performance. However, site validation is vital for confirming the modeling outputs. For every work that I've used, I made sure there's good correlation between the site measurements and the modeling results, because this will give me confidence to make changes to standards, processes, and drawings. The example shows tangible benefits in terms of we identified the failure modes and developed solutions for it. We improved the standards, drawings, and processes, and we improved track designs for easier installation, lower cant that is, and reduce maintenance and therefore lower whole life cost. We have good engagement with suppliers to ensure better quality of products and consistent production processes to improve asset performance. And most importantly, we have safety by design. We make sure we design something that's safe, that we put on track, and it will work. Thank you.